great to start your day with infinity? Yeah? I hope you had your coffee. Okay, so we're going to take a look at another example here. Sine x over x as x goes to infinity. If you look down the picture, you'll see that this goes towards 0. And again, the idea is I keep saying Bill Gates, and I hope you remember that because it is useful to think of the theory behind this concept, right? So what's going to win out, sine x or x? Think about those two graphs. As x gets very, very large, compare that to the sine of x. How big, what's the biggest thing that sine x has to compete with?
1.
Yeah, so it's like x pulls out a 10, and sine x is like, haha, I have a 1. I can't compete. There's nothing I can do to compete. X pulls out 100, and sine x still only has a 1. Right? So it's kind of like if you're playing like Call of Duty or something, you have like a stick, and your opponents have the M16 or whatever it was, right? You picked up a rock off the ground. So you're probably not going to win. But how can we prove this? Well, we could prove this by saying this is one way we could squeeze the graphs. Okay? The sine of x, it can at most go between -1 and 1. So that means I could squish these three together, and they're going to represent a way we could do this with squeeze theorem. Okay? So if we take a look at the limit as x goes to infinity, okay, what's going to happen to the first piece? Yeah, it would be going to 0. And the second piece is also going to 0. So therefore, this limit is equal to 0. Okay? So again, you're not ever going to be expected to pull out the squeeze theorem on a test and, show some beautiful proof of something like that. But it's always good to know where these things come from. You should know this one as well. Sine x over x goes to 0. And again, if you don't do a full proof of it, just think like Bill Gates would, right? You can pull out $1, but Bill Gates can pull out billions, right? So he's going to win, okay? So what do you think? What limit will we get? Can you figure out, using our new little piece of information, sine x divided by x, what would you come up with for this limit? Okay, so if we're doing this one, students often lose sight of the fact that you can separate limits, right? There was a time when we said, here's the limit laws. You can do them just like normal arithmetic. So it's easier sometimes to think about these two pieces than to think about, than to think about the whole thing together. Okay, so I know that this is going to approach 5, this is going to approach 0, so this limit should be equal to 5. Okay, so it's good to see that some of you had caught on to that, but that is a good strategy. If it's too hard to do all in one piece, break it up. Okay, so the last thing that we want to look at here are some limits when we end up using trig functions. Yeah, I know. Awesome, isn't it? We talked about these ones, right? So what is the arc cotangent? Does anybody remember what the arc cotangent is? It's been a while? Yeah, it's been like 5 days, so. Can anybody give me one thing that's important to know about the arc cotangent? Yeah?
It's like only the certain section of the graph?
It's only from one piece of which graph?
The
Cotangent, yeah, it's only a part of the cotangent. And the reason that we didn't want to go too far was that we wouldn't get an inverse. So the reason it's only part of the graph is this is trying to get us back to the between cotangent and tangent. So remember, this is the one you think of as the inverse cotangent. Okay, so why don't we bring up the cotangent graph just so you guys can familiarize yourselves with it. So if you were to forget what was the arc cotangent, you could take a look at the cotangent graph. And of course, we want to shrink that range down. Okay, so there's the cotangent graph. which right now would not give me an inverse function. It does not pass the horizontal line. So what did we have to do to get an inverse function out of it?
Eliminate, hey, we need all but one period.
Right, we wanted one period of the graph. So what do you think would be a natural choice looking at this picture?
The one in the top, to the right of the y-axis.
The one to the right, which goes from 0 to pi. So that's the choice that is used. So there's the arc cotangent graph, or sorry, there's the cotangent graph. If I wanted to see, well, what does the inverse look like? Well, it's kind of strange because it's chopped off right now. So I'm going to split up this graph a little bit just so you can see it better. And, oops, that wasn't an equation. X equals cotangent of y. Cotangent, okay, and I'm going to take a look at y equals cotangent x from 0 to pi. So it's hard to see it, but there is still a reflection happening there. And the interesting thing is, let's get rid of this last graph. You can see there are horizontal asymptotes here, right? Okay. So usually you don't have time to refer and make all these sketches up, so I'm going to show you how I deal with these inverse graphs when I'm doing it in a question. I'm going to go back to the cotangent of x, and we were only dealing with the piece of it here. Oops. And that was 0 to pi, and let's go something like that. Okay, so here's what we're thinking of. If I'm going towards infinity, right, that example is going towards infinity for x. Where am I going on the graph that's pictured up there, the cotangent graph? If x goes to infinity, how could you word it? What am I looking at in this picture? So if I'm on x in the function, what am I talking about in the inverse? Y. I'm talking about y in the inverse graph. So as x goes to infinity, an arc cotangent, that's the same thing as saying where does y go to infinity on the, yes, cotangent. Sorry, brain froze there for a second. Okay, so what happens? What value am I approaching there as for x when y goes towards infinity? Yeah, that's what it's hard to see. Maybe if I zoom out more, let's go like negative 20 to 20. Will that be better? So as I get closer and closer to infinity, which is up here for y, the value of x is getting closer to 0. So we're flipping it backwards. You can do that in this limit here. You could split this up and say, let's take a look at the limit as x goes to infinity of two pieces. The limit as x goes to infinity of the arc cotangent x. But this is the one that makes you go, huh? That's hard. Let's change this so that we can think about it in terms of a cotangent. So we noticed when we saw this that as y went towards infinity, the y coordinate was jumping all the way up to infinity, that x was approaching 0. Okay. So that's what would happen in reverse when I put it into the inverse. As x goes to infinity, the y coordinate goes to 0. So this one here would also go off to 0. Okay. So that means I would have this limit, which hopefully you guys, that's not so scary. What's the limit of 7x over 3x squared going to be?
0.
Yeah, that's going to be 0. The scary one that we just talked about went towards 0. So we could say that asymptote did go towards 0. Okay, so you try the next one on your own. If we're going towards negative infinity for x, your job is to think about what am I approaching as I go towards negative infinity for y. Okay.
Graph this.
Where's the arc button?
There, you can graph the arc cotangent. Anyways, I'll help you with that once we get the lesson over with. But this piece here, we'd be talking about the limit as x goes to negative infinity of 7x over 3x squared minus the limit as x goes to negative infinity of the arc cotangent. So I don't have the graphing calculator up here, but here's the arc cotangent graph again. Okay, so this is pi. This is 0. So when x is going to negative infinity in the arc cotangent, that means I'm looking at the y-coordinate going to negative infinity in the inverse, right? X and y are switched. So if y is going to negative infinity, the value I'm approaching is pi. Okay, so this here would end up going towards pi, and this one would still be 0. So this limit would be negative pi. Okay.